Welcome to Deep Dive Lab, where we break down and dissect cutting-edge scientific research, from advanced biomedical technologies to breakthroughs in AI, material science, chemistry, and physics, all told as compelling, easy-to-follow stories. And today we are talking about time.
Yeah, a really massive topic.
Right. And, if you watch movies like Interstellar or Back to the Future, time manipulation is always this, massive plot point.
Oh, totally.
You've got astronauts on that water planet where, 1 hour equals 7 years on Earth because of a black hole. Or, you need a DeLorean hitting 88 miles per hour to jump through decades.
Right, classic.
But the wild thing is, you actually do not need a black hole or a time machine to experience time differently. In fact, right now, as you are listening to this, your feet are literally aging at a different rate than your head.
I mean, I know it sounds like total science fiction, but it is an absolute measurable fact of our universe. Gravity warps time.
Just natural.
Exactly. The closer you are to the center of the Earth, the stronger the gravitational pull and the slower time moves. So your feet being slightly closer to the ground than your head, well, they're experiencing time just a tiny fraction of a second slower.
Which is just, that's mind-blowing. But at its most basic level, right, any clock is just something that ticks. Like a pendulum swings or a quartz crystal vibrates.
Yeah, exactly. It's an oscillator.
Right. So building an atomic clock is basically like tuning a generic instrument. Imagine you have a standard macroscopic oscillator, something in the everyday world that vibrates, like that quartz crystal or a laser.
Right.
That is your generic guitar. And you need to tune it to a perfectly pitched tuning fork. And in the realm of physics, that perfectly pitched tuning fork is a precisely defined atomic transition.
Yeah, and to kind of unpack that atomic transition a bit further, you have to think about an atom as like a tiny solar system. You have a nucleus in the center and electrons orbiting around it. And those electrons can only jump from a low-energy orbit to a higher-energy orbit if they absorb the exact right frequency of energy.
Exactly the right amount.
Right. Not a little bit more, not a little bit less.
Yeah.
That sharply defined energy difference between two states of an atom is a fundamental, unchangeable rule of quantum mechanics.
I see.
So you are taking your everyday oscillator, your laser or your microwave generator, and just adjusting it until it perfectly matches that quantum jump.
Okay, so here's a strange question. Why does time actually change depending on where you stand? And how on earth did scientists figure out how to measure a single second so precisely that they could even notice?
That is the big question.
Because we aren't talking about a regular stopwatch here. To understand how scientists are now literally trapping atoms with light to measure time, we have to look at what they were originally dealing with. Like, what is a second, really?
Well, if we look at the current standard, which was established decades ago, the official definition of the International System of Units, the SI second, is exactly 9,192,631,770 ticks.
Wait, ticks?
Yeah, periods of radiation of a cesium-133 atom.
Okay, over 9 billion ticks in one single second.
Yeah, it's incredibly fast. And for a long time, scientists measured those ticks using these early microwave beam clocks.
How did those work?
Basically, they would take hot cesium atoms and shoot them through a microwave cavity to interrogate them.
Interrogate them? You mean like measure them?
Right, measure them. But the problem is trying to measure an atom's incredibly fast vibrations while it is hot and moving hundreds of meters per second. It's really difficult.
Yeah, that is like trying to read the tiny expiration date on a license plate on a car speeding past you at 200 miles per hour.
Exactly.
You just don't have enough time to get a good look before it's completely gone.
Right, and the shorter the time you have to look at that license plate, the less accurate your reading is. In physics, we call that a limitation on your interrogation time.
Okay, that makes sense.
So to get a better look, scientists had to find a way to slow the atoms down. And they achieved this using laser cooling.
Okay, wait. I always get tripped up on this concept because you usually think of lasers as things that, heat stuff up or burn through metal.
Right, like in sci-fi movies.
Exactly. So how does firing a laser at an atom actually cool it down?
Well, it comes down to momentum. Even though particles of light, photons, do not have mass, they actually do carry momentum.
Okay.
So imagine an atom is a bowling ball rolling toward you, and you start shooting a barrage of ping pong balls at it.
I'm picturing it. Just hundreds of ping pong balls.
Right, and each individual ping pong ball doesn't do much, obviously, but millions of them bouncing off the front of the bowling ball will eventually slow it down.
Oh, wow.
Yeah, so by firing carefully tuned lasers at the cesium atoms from all directions, the atoms constantly absorb and emit photons, and they lose their forward momentum.
Then that cools them down.
Exactly. Because in physics, temperature is just a measurement of how fast atoms are moving. So by slowing them down, you are literally cooling them to just a few microkelvin above absolute zero.
Which creates a state where the atoms are just incredibly sluggish.
Right.
And that breakthrough led to what we call fountain clocks, right? Like the NIST F1 primary standard.
You've got it. You take these super-cooled, sluggish cesium atoms, gently toss them up into a vacuum chamber, and just let gravity pull them back down, literally just like water in a fountain.
Oh, so that's why they call it a fountain.
Exactly. By tossing them vertically, the atoms pass through a microwave field on the way up, and then they fall back through it on the way down.
Okay, I see.
And because the atoms are moving so slowly now, your interrogation time, the time you get to stare at the license plate, is much longer. These cold atom fountains hit fractional uncertainties in the low 10 to the minus 16 range.
That is a lot of zeros.
Yeah.
And to keep things stable in the short term, laboratories paired these fountains with hydrogen masers, right?
Yes. The hydrogen maser acts as a superb flywheel.
A flywheel.
Yeah, so while the cesium fountain provides that ultimate long-term accuracy calibration, the actual measurement process takes time. You need something to keep the beat steady between the fountain's measurements.
Like a metronome.
Exactly. So a maser uses hydrogen gas in a microwave cavity. When the hydrogen atoms drop from a high-energy state to a lower one, they emit a microwave photon.
Okay.
That photon bumps into another atom, causing it to emit a photon in perfect sync, and so on. It creates a continuous, incredibly stable microwave hum that bridges the gaps between the fountain's measurements.
But even with all that, the laser cooling, the fountains, the hydrogen maser flywheels, they basically hit a roadblock around the 2010s.
Yeah, they really did. The machinery was practically flawless, but they just couldn't measure time any more precisely.
Because of the microwaves.
Right. The issue is the frequency of the microwaves themselves. I mean, around 9 billion ticks per second is incredibly fast. But if you want to slice time even thinner, microwave frequency simply runs out of resolution.
So how did scientists figure this out? Like, how do you slice a second thinner than a microwave? Because this is where the story gets really interesting.
Well, they initiated a complete paradigm shift. They moved from microwave frequencies to optical frequencies.
Optical, so like light.
Yes. Instead of interrogating atoms using microwaves,
Yeah.
scientists started using lasers in the optical domain, the visible light spectrum.
Which operates at a massive frequency, hundreds of terahertz, I think.
Exactly. That is more than 10,000 times higher than the microwave clocks.
Oh, wow. So if a microwave clock is like trying to measure a distance with a clunky yardstick, an optical clock is like using a microscopic micrometer.
That's a great way to put it.
You can just see fractions of a measurement that the yardstick completely glosses over.
And the results of this shift have been staggering. I mean, according to a major review published in the journal Reviews of Modern Physics by Dr. Ludlow and his colleagues back in 2015, and there's more recent studies in Physical Review applied in 2022. Scientists at institutions like NIST, the University of Tokyo, and Riken have developed two main architectures for these new optical clocks: trapped ion clocks and optical lattice clocks.
Let's break those down. In a trapped ion clock, they isolate a single ion, often aluminum or ytterbium or calcium, right?
Yeah.
And they suspend it in a vacuum using electromagnetic fields. Because it's just a single isolated ion, it is incredibly protected from outside interference.
Exactly. And the aluminum ion clock at NIST reached a systematic uncertainty of about 9.4 times 10 to the minus 19.
Which means it is one of the most accurate clocks ever realized.
Yes, but the fundamental challenge with that architecture, however, is a phenomenon called quantum projection noise.
Quantum projection noise, that sounds intense.
It sounds complicated, but basically when you interrogate a quantum system, you only get a limited amount of information per measurement.
Okay.
So if you're only looking at one single ion, you have to measure it over and over and over again for a very long time to average out the statistical noise and get a clear signal.
Oh, I get it. It's like trying to judge a song by listening to a single singer who sometimes sings a bit too quietly.
Right.
It takes a while to figure out the actual melody. But if you have a whole choir singing the exact same note, the signal is booming and you instantly know if they are in tune.
Yes. And that brings us directly to the second architecture, the optical lattice clock.
The choir.
The choir, exactly. Instead of trapping one ion, an optical lattice traps tens of thousands of neutral atoms, typically strontium or ytterbium.
How do they trap thousands of atoms at once?
It uses intersecting laser beams to create a standing wave of light. Think of the peaks and valleys of a corrugated metal roof. but made entirely of pure energy.
Okay, a metal roof made of light.
And the atoms sit nestled in the little valleys of this light web. Because you have thousands of atoms you acquire, the signal is incredibly strong and stable almost immediately.
Okay, wait, I have to push back on this.
Sure.
We just established that atoms are incredibly delicate.
They are.
If you are trapping thousands of strontium atoms using intense, powerful intersecting lasers to create this, like, egg carton of light, wouldn't the laser light itself completely scramble the atoms?
That is a very logical question.
Right. You're bombarding them with photons.
Yeah.
Wouldn't that change their energy levels and ruin the atomic transition you are trying to measure in the first place?
It absolutely does, or at least it can. This is a major hurdle in physics known as the AC Stark shift.
The AC Stark shift.
Yeah, the intense light of the lattice absolutely perturbs the atoms. It changes the energy of their ground state and their excited state.
Which messes up the clock.
Exactly. And for a long time, many assumed this would make an optical lattice clock inherently flawed. But scientists discovered a brilliant workaround called the magic wavelength.
The magic wavelength. Okay, what exactly makes it magic?
It is a very specific, carefully calculated frequency for the lattice laser. When you tune the laser to this exact magic wavelength, the light's disruptive effect on the atom's ground state perfectly equals its disruptive effect on the excited state.
Oh, so they cancel out.
Yes, the two shifts move in perfect tandem.
So it's like putting a ship on a river. The river's current is pushing the hull downstream, but the wind is pushing the sails upstream with the exact same force.
I love that analogy.
The ship doesn't move. It is suspended perfectly in the water, even though two massive forces are acting on it.
That is a perfect visualization. The atom is securely trapped by the intense light, but the energy gap, the transition frequency between the two states that we actually use to measure time, remains completely unchanged.
As if the laser wasn't even there.
Exactly. And this breakthrough allowed researchers at the University of Tokyo and Riken to pull off one of the most remarkable experiments in modern metrology.
What did they do?
They built two different optical lattice clocks, one using strontium atoms and one using ytterbium atoms. Then they compared the tick rates of these two different elements to establish their frequency ratio.
And their findings, what happened?
They determined that ratio with an uncertainty below 5 times 10 to the minus 17.
Okay, for you listening, we really need to pause and emphasize what that actually means.
It's huge.
They measured the time difference between these two clocks so precisely that their measurement was actually more accurate than the official definition of the SI second itself.
Right.
I mean, the tools they were using to measure the time were sharper than the universe's official ruler for time.
Exactly. It proved definitively that optical lattice clocks have surpassed cesium microwave fountains by roughly 2 orders of magnitude in both accuracy and stability.
Wow.
And because of this, international metrology bodies are actively preparing to officially redefine the SI second based on optical transitions. It will be the first time the fundamental unit of time is redefined in over 50 years.
That is wild. But, if these clocks are this sensitive to the tiniest changes in their environment, how do we actually use them outside of a perfect, isolated laboratory?
That is the next big challenge.
Because precision timekeeping is basically the invisible infrastructure of the modern world.
Wow.
Take your phone's GPS. The global navigation satellite systems rely on atomic clocks broadcasting from space, and most of those satellites currently use rubidium microwave clocks.
Yeah, rubidium secondary standards offer a great balance of good stability with a really compact size, lower power consumption, and lower cost. They are essentially the workhorses in space.
Yep.
So when you use your phone's map to find a coffee shop, your phone is calculating its exact position on Earth by measuring the time of flight of the signals arriving from those rubidium clocks in orbit.
Right, so better clocks mean better GPS. But it goes way beyond navigation.
Oh, absolutely.
High-frequency stock trades, telecommunications networks, the global power grid, they all rely on atomic clock synchronization. If those clocks drift even a fraction of a microsecond, systems fail.
Right.
But the catch is, you can't build a massive vacuum chamber and laser array inside a standard cell tower.
Which is exactly why the miniaturization of this technology is so crucial. NIST and other labs have developed chip-scale atomic clocks, or CSACs.
CSACs.
Okay. Yeah, through microfabrication, they basically etched the essential components, a tiny Weber cell for the atoms, a microscopic laser, and miniature microwave antennas right into silicon wafers.
Wait, they shrunk the entire physics package down to the size of a grain of rice.
Yeah, a package about 1.5 millimeters on a side, consuming less power than a small light bulb, yet offering atomic-grade timing.
That is incredible.
It really is. This means you can have atomic precision in an underwater drone mapping the seafloor, or deep underground in a mine, or in a secure communications network where standard GPS signals are blocked or jammed.
And the optical clocks.
Researchers are already working on next-generation chip-scale clocks that use those optical transitions, which will offer even greater stability in that exact same tiny footprint.
But the applications get even wilder when we look at those ultra-precise optical lattice clocks back in the lab. This brings us to a field called chronometric geodesy.
Which sounds intimidating, I know.
It does, but it basically means using time to measure the physical shape and gravity of the Earth.
Right. Remember our opening discussion about gravity warping time?
Yeah, your feet aging slower than your head.
Exactly. Because these optical clocks are accurate to the 18th decimal place, they are hypersensitive to the gravitational potential of the Earth.
Okay.
So if you take one of these optical clocks and lift it just 1 centimeter off the table, the Earth's gravitational pull weakens just enough that the clock physically ticks at a measurably different rate.
Just 1 centimeter changes how it experiences the flow of time. That is insane.
It is.
That means they aren't just clocks anymore. They are literally the most precise gravity and elevation sensors ever created.
You got it. By comparing optical clocks at different locations via stabilized fiber optic networks, scientists can directly measure the minute differences in Earth's gravity field between those two spots.
So you could, place these clocks around a volcano, and by watching how their timekeeping slightly speeds up or slows down, you could detect the movement in a massive magma chamber shifting deep underground.
Exactly. Because the magma changes the local gravity, which changes the flow of time.
You could monitor the depletion of underground water tables during a drought, or watch the tectonic plates slowly grinding together before an earthquake, all just by measuring time.
It completely flips the concept of a clock on its head.
Yeah.
And it goes even further than the Earth. Scientists are now designing space-qualified optical clocks to shoot into orbit.
Okay, I still don't get this part.
Why not?
We just established that moving a clock 1 single centimeter messes up its tick rate because of gravity.
Right.
Space is a chaotic gravitational environment. You have the Earth, the Moon, the Sun, all pulling on a satellite moving thousands of miles an hour. Why on earth would you strap a hypersensitive optical clock to a rocket and shoot it into that mess?
Well, to hunt for new physics and
Yeah.
test the very boundaries of our understanding of the universe. By creating a global and eventually solar system-wide network of optical clocks, physicists can test Einstein's general relativity with unprecedented stringency. And furthermore, they're using these networks to hunt for ultralight dark matter.
Wait, how does a clock hunt for dark matter? Dark matter doesn't interact with light.
It doesn't interact with light the way we traditionally think of, no. But the current theory is that if the Earth passes through a massive field of ultralight dark matter, that field could cause temporary glitches in the fundamental rules of the universe.
Glitches in the rules? Like what?
For example, it might slightly tweak the fine structure constant,
Which is...
which is essentially the dial that controls the strength of electromagnetism. It dictates how tightly atoms hold onto their electrons.
Oh, okay.
If dark matter turns that dial even a fraction, the energy gap inside our atomic tuning fork shifts, and the clock's ticking would briefly flutter.
Oh, wow. So by linking clocks made of different atoms, say strontium in Tokyo and ytterbium in Colorado, scientists can look for correlated flutters in the network. If both clocks glitch in a specific pattern at the same time, it isn't an error. It's the footprint of dark matter washing over the planet. The clocks become a planet-sized antenna for invisible particles.
It really is beautiful, and humanity's quest to simply build a better metronome, to just count the seconds more accurately for our own coordination, we accidentally built a telescope that can sense gravity and a trap that can detect dark matter.
We have covered a massive amount of ground today. Let's bring it all together.
Let's do it.
We started in the microwave era, reading fast-moving cesium atoms to define our standard second. Then we made the massive leap to optical frequencies, figuring out how to freeze atoms using the momentum of light and trapping them in magic wavelengths that perfectly balance out disruptive forces.
Slicing the second 10,000 times thinner.
Exactly, which has pushed the international community to the brink of officially redefining the SI second for the first time in over half a century.
It's an incredible milestone.
And finally, we saw how this mind-bending precision means these devices have evolved. From chip-scale clocks guiding drones through the deep ocean to chronometric geodesy mapping volcanoes, they are no longer just timekeepers. They are literal sensors of the universe's fabric.
Very well said.
So if this discovery is just the beginning and lifting a clock 1 centimeter changes how it experiences time, what might scientists uncover next when we string these optical clocks across the solar system?
That is the exciting part.
Thank you for joining us in Deep Dive Lab. If you want to keep unraveling the mysteries of the universe with us, be sure to follow and subscribe for more science stories. See you next time.